vector space V has a basis B1 to Bn, meaning there's n vectors in it, then any set in V that contains more than n vectors must be linearly dependent. Okay. If a basis has n vectors in it, what is the dimension of the space? N. And what day is it? Thursday. All right, so specifying a basis for a vector space allows us to impose a coordinate system on the vector space. So think about like the Cartesian coordinate system. That is imposing the basis 1, 0, 0, 1. So we plot all points by saying how far do you go in the 1, 0 direction, how far do you go in the 0, 1 direction. And we call that the standard basis for R2. But 1, 0, and 0, 1 are somewhat of an arbitrary choice. It feels natural because you use them all the time. But you can pick any basis in R2 to be your coordinate system. So for example, let's use an alternative basis, and we'll call it gamma 1, 0, 1, 2. So any vector in R2 can be written as a unique linear combination of the vectors in the basis. So let's look at the vector 7, 4. If we're using the standard basis, I just have to figure out what weights do I put on my basis vectors to build the vector 7, 4. So this feels kind of stupid when you're using the standard basis because we're like really used to it. And we strategically chose 1, 0, and 0, 1 as the standard basis because then 7, 4 is just 7, 4, right? So your weights are 7 and 4. Right, so 7, 4, the vector 7, 4 in R2, if you were to write that as the coordinates of x with respect to the basis beta, it would be 7, 4. So under the coordinate mapping determined by the standard basis beta, 7, 4 is just 7, 4. But if we use the alternative basis, we're saying, okay, I want to build 7, 4 using these two vectors as my basis. Like what weights do I have to put on those basis vectors to build 7, 4? What? 5 and 2, yeah. Yep. So you have 5 plus 2, that gives you the 7, and then 0 plus 4, that gives you the 4. 5 and 2. So the coordinates of the vector 7, 4 with respect to the basis gamma are 5, 2. So under the coordinate mapping determined by the alternative basis gamma, 7, 4 goes to 5, 2. So to just give this some visual context, coordinate systems are so that you can plot your vectors. Right? So under the standard basis beta, to get to the point x, you go 7 units in the 1, 0 direction, 4 units in the 0, 1 direction, and you land at the point 7, 4. But if I use the alternative basis gamma to arrive at that same point, right, I'm going to land in the exact same spot, but I'm going to go 5 units in the 1, 0 direction, 2 units in the 1, 2 direction, and I'm going to land in the same place. 5 units in 0, 1. And then I drew in the line, one line that's in the 1, 1, 2 direction. And each time you go over 1 and up 2, that's 1 unit in the 1, 2 direction. So if I go over 5 in the 1, 0 direction and then 2 units in the 1, 2 direction, I land at the point 5, 2 with respect to the basis gamma. But you can see it's the same point as if I went 7 units in the 1, 0 direction and 4 units in the 0, 1 direction. You land at the same place. So it's just saying we could make the basis, if you you could choose any basis and get to the same point by going a certain distance in one direction and then a certain distance in the other direction. You land in the same place. So 1, 0, and 0, 1 aren't necessarily arbitrary. We chose them because they're the most convenient, but you can choose any basis for R2 and use it as your coordinate mapping system. All right, so here's the notation. We've got a basis beta for R3. So I'm telling you that this is a basis. The standard basis for R3 would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's the X, Y, Z direction. But I've given you an alternative basis for R3. So that's telling you that this is a linearly independent set that spans all of R3. All right, so I'm telling you that the coordinate vector with respect to of x with respect to the basis beta is 1, 0, 4, and we want to find x. So this is the weights, right? If you go back to what we did over here, this notation is the weights. These are the weights that you put on the basis. So we're being given the weights that you put on the basis. So we put a 1 on the first vector of the basis, a 0 on the next vector, and a 4 on the last vector. And we get x. And when you say just a plain old x in R3, that's with respect to the standard basis. That's just a regular x, y, z. So this would be -2 minus 4 is -6. -5 minus 8 is -13. And 7 minus 4 is 3. This is just our standard x, or I could write it as this is the coordinate of x with respect to the standard basis, which I usually call beta, but I'm going to just write standard basis. So that's the 1, 0, 0 direction, the 0, 1, 0 direction, and the 0, 0, 1 direction. All right, so now I want to find the change of coordinate matrix from beta to the standard basis. That's just your basis in a matrix. So you can see if I were to put 1, -4, 4, and -1, -2, -1, if I put them in a matrix, and then if you multiply by this will take you beta to the standard, from beta to the standard matrix. So if you multiply by coordinates with respect to beta, 1, 0, 4, do that multiplication out, you should get -6, -13, 3. So just an alternate way of converting. So you can either remember that this notation is weights that you put on your basis, or you can make a change of coordinate matrix. Okay, so now I want to find, I'm looking for x sub beta, right? So I'm looking for the weights. In the last question, I spelled that wrong. In the last question, they gave me the weights, and I just put them on the basis and added it up, right? Now they're saying, what are the weights that will give you 529? So I'm going to say, all right, what weights do I put on my basis vectors? x1 times -2, -5, 7, plus x2 times 1, -4, 4, plus x3 times -1, -2, -1. What weights will give me 529? So 529 is just normal. That's like with the standard basis and the XYZ basis. And what weights x1, x2, x3, those would be the coordinates if I redefined the coordinate system using this alternate basis. So how would I solve this? RREF, yeah. So I'm just going to augment, put these together in a matrix, augment with 529, and row reduce. Oops. And I get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 4 thirds, negative 11 thirds. So that is my coordinates of x with respect to the basis beta. All right, I'm just going to answer this exact same question again, but using an inverse matrix. So an alternate way of writing this vector equation would be as a matrix equation, where I put my matrix A times my unknown weights to build my 5, 2, 9. That is equivalent to the vector equation from above, and it's would translate to the augmented matrix that we used to solve. So another way to solve this equation, rather than RREFing, is to multiply both sides of this equation by A inverse on the left. So I could find A inverse on my calculator. Everybody remember how to do it? Yeah? Okay. You put A on, you have to make a 6 by 3 matrix. Nope, 3 by 6. 3 rows, 6 columns. You put A in the first half, you put the identity in the second half, and then row reduce, and they swap. So A inverse times A cancels, and we get x1, x2, x3 is isolated on the left. A inverse, I did it already, it's ugly, negative 4/17, 19 over 51, negative 8 over 51, 1/17, negative 3/17, negative 5/17, 2/17, negative 1 over 51, negative 13 over 51. That's A inverse. Multiply that by 5, 2, 9, and you get 0, 4 thirds, negative 11 thirds. So that was just to remind you of that alternate way of solving a system. All right, so P3, this is the set of all polynomials of degree 3 or less. Its standard basis is 1t, t squared, t cubed. Just throw some weights on those 4 things, add them together, and you've got a polynomial of degree 3 or less. So a typical element in P3 would be a0 plus a1t plus a2t squared plus a3t cubed. So a0, a1, a2, and a3 are just your weights. Those are the weights you throw on the basis vectors, you add them together, you get a typical element in P3. So my coordinate vector with respect to the basis beta is just a vector of weights, right? It's just a vector of weights that you put on the basis. So it would look like this: a0, a1, a2, a3. And that looks like a vector in R4. Yeah. So what easy to work with vector space is P3 isomorphic to? R4. And we know so much about R4, right? We've been doing things with R4 all semester, or any RN, right? So we have this now coordinate system that we can impose on P3 that lets us work in R4, answer whatever question they asked us about P3, answer it in R4, and then that answer also applies to P3 because R4 and P3 are isomorphic. Okay. So what that means is that they are, in practice, it means they are essentially the same. Any question you answer about R4 also applies in P3. So they are essentially the same. Right? That's what isomorphic should mean, like in your working brain. The definition is that there is a coordinate mapping from R4 to P3, which we just showed.